Hello everyone, I'm Dr. Redwan Alqasemi, Robotics Professor at the University of South Florida. And today I'm going to talk about Chapter 7, Trajectory Generation. We're not going to cover the whole chapter in the reference book, but we're going to cover some aspects of the chapter in a slightly different way. And the main purpose of this is just to get some simulation going. So we need the trajectory to realize the simulation. So in summary, we're going to learn how to create Cartesian trajectories and joint trajectories. Cartesian trajectories are for end-effector Cartesian coordinates, and joint trajectory for the joint domain for each joint of your robot. Our learning objectives today learn the difference between the linear and the polynomial trajectories. So each one of these two would look different in terms of position, velocity, and acceleration. We're going to also learn about how to find a discrete trajectory or a continuous trajectory equation. So discrete trajectories are dealing with via points. Continuous trajectories are equations that you can just substitute the time to find where your points in that trajectory that you're interested in. And then finally, we're going to look at the Cartesian orientation trajectories. These are not covered in the textbook. And basically, this is when you have a trajectory for orientation that deals with rotation matrix or alpha, beta, gamma orientation variables. So these are completely different ways to find the trajectories, and we're going to cover that in this video. To get started on this chapter, I'm going to introduce two different trajectories that are commonly used in simulation. So these trajectories are valid for joint motion or end-effector motion in space. So it can be used either in the joint domain or the Cartesian domain. And these two trajectories that are commonly used in simulation are the linear trajectory and the polynomial trajectory. So from this figure here, I'm going to look at both of them and compare them side by side. So the linear trajectory here on the left and the trajectory with polynomial on the right side. And here I'm plotting the position, velocity, and acceleration of these joints. So if we look at the linear trajectory position, and just as an example here, I put theta, but this can be either theta from joints or it can be xyz from the Cartesian coordinates. So the linear trajectory looks like this. So it starts at initial time frame at theta initial and then goes in a linear fashion to theta final at a final time frame. So this plot here shows the time versus position. And if you look at the velocity profile, it looks like we're going to have a constant slope here, which means that we have a constant velocity. And that constant velocity translates into zero acceleration. So if you notice here for this case, for example, because we're using simulation, it's possible to do such a case. If you start at initial position as 0, and then you go from 0 velocity to whatever velocity that you have here, okay? And you're doing this, as you can see, you're doing this in no time, which means that the acceleration goes up to infinity at this particular initial period, okay? And then goes back down to 0. And then when you want to stop, that velocity goes from whatever value down to 0 in no time. So that means you have infinite deceleration at this point. So this is impossible to do because we don't have infinite torques in our motors if you're using this for physical systems. But in simulation, this is possible. So that's why we included it here. And that's widely used and commonly used in simulation. Now, the other kind of trajectory that we're going to cover here is the trajectory with polynomial. So instead of having a linear profile for the joint motion, we have a polynomial profile, as you can see here. So we start at initial theta, let's assume it's 0, and then we gradually start speeding up to whatever maximum velocity that we want, which is right here in the middle of that time period. And then we start slowing down into our final position. Okay, so that gives me that look profile for the position. And if you look at this, the slope of this curve is changing with time. So initially it's going at a steady slope change here, and that would be a constant slope for the velocity profile. And then at this particular point, we switch from increasing velocity to decreasing velocity. So that slope basically switches back down into the slope that we see here. Now, since this velocity profile is having constant slope for this curve, that means we have also constant acceleration for this particular period. Again, we're going here from this velocity to whatever maximum velocity, but we're doing this in time. So we don't have that infinite acceleration, but we're suddenly, going acceleration from 0 to whatever value here, and then switching down the acceleration to deceleration at the midpoint, and then going back to 0 acceleration at the end of the time. So this here particular trajectory is a little bit better than the linear trajectory, but at the same time, for simulation purposes, the linear trajectory is sufficient to provide us a simulation. Now we can go further from here. We can go with second degree, third degree, fourth degree polynomials, but in this case, this is good enough that we want to cover in this chapter. In this course, we're going to talk about only linear trajectories. We're not going to talk about polynomial trajectories. So in this slide, I'm going to cover joint trajectories. That's in the joint domain, not in the Cartesian domain. So this is linear trajectory for joints. And the linear trajectory for joints is going to be divided into two different segments. The first segment is discrete trajectories, which means that we have via points. So these are points along my trajectory that I need to pass through in order to reach my final destination. And usually in such a case, for any particular joint in my robot, I will be given theta initial and theta final and the number of steps. So these are part of the design for my trajectory. And then I will find a theta step, which is basically the final theta minus the initial theta divided by the number of steps. Once I find my step distance or angle, then I can go on to construct my trajectory, starting with theta initial, then going to the next step, which is theta initial plus theta step, and then the next is theta initial plus 2 theta steps, all the way until I reach my final theta. Okay, now remember, all this trajectory here is for a single joint in my robot. If my robot has multiple joints, I'll have to repeat this step until I find the trajectory for all of my joints. So this procedure basically can find you multiple trajectories for your robot so that each one of the joints can follow its own trajectory. The other segment for the linear trajectory for joints in the joint domain is the continuous trajectories, which are basically equations of lines, and these equations are our definition of each one of the trajectories for each one of our joints in the robot. In this case, we do not have via points as the previous case in the discrete trajectories. And here we have equations that define a solid line. Again, the given information is theta initial and theta final. And then here we have the total time to go from theta initial to theta final, as opposed to the previous slide where we had discrete trajectories, we had the number of steps. Here we have the total time, not the number of steps. Once we have this information, we can find the joint velocity, which is theta dot, which is theta final minus theta initial divided by total time. And in this case, the acceleration will be 0 for the joints. So now we are ready to create the trajectory equation for this joint. In this case, theta equals to theta initial plus theta dot times t, where t is the time at any instance. So this is a linear equation of a first order, and basically if we need to find theta, the position of theta at any moment in time, all we have to do is substitute that time here, and we can multiply that by theta dot, which is already found from the previous step, and then add to that theta initial, which is a given information. So at any moment in time, I can find out where my theta is in the trajectory. Now remember, this is going to cover one joint in my robot. If I have multiple joints, then I have to do the same thing, repeat it for each one of the joints until I have all the equations for each one of the joints that would define my joint trajectories. The previous slides cover the linear trajectory for joints in the joint domain, and here we're going to discuss the linear trajectory for Cartesian coordinates of the end-effector. So this is the Cartesian domain that we're going to be discussing in this section. Now again, this section is also divided into segments, 3 segments. The first segment is the XYZ coordinates with discrete trajectories. So that's a via point discrete trajectories. In this case, we use exactly the same method as the methods we used for joint trajectories. So here, given x initial, x final, and the number of steps n, we can find the trajectory step or x step, which equals to x final minus x initial divided by the number of steps n. And then we can construct our Cartesian trajectory for x, which starts with x initial, and then the next step would be x initial plus x step, and then x initial plus 2x steps, and then so forth until we get to x final. Now remember, this is only for the x coordinate of the Cartesian coordinates for the end-effector, and then we can repeat the same thing for the y coordinate and for the z coordinate. So we have to repeat this twice after the step, and then that would give us a total of 3 trajectories that cover x, y, and z in our Cartesian coordinates of the end-effector. The second segment we're going to cover about the linear trajectory for Cartesian coordinates of the end-effector would be the x, y, z coordinates continuous trajectories. So again, these trajectories are equations of lines that define the trajectory as opposed to via points. Again, the given information is x initial, x final, and the total time that takes us from x initial to x final. And then we are ready to find the velocity of the x coordinate. So x dot equals to x final minus x initial divided by t total. And in this case, the acceleration of x is x double dot, which is 0. Now we're ready to construct our equation for the trajectory in x, and that would be x equals to x initial plus x dot times t. So at any moment in time, if we would like to find where x is of our end-effector, at any moment in time, we can just substitute that time here, and then x dot is already known from the previous step here, and then x initial is a given information that we have it by design, and that would give me x at any moment in time. Now remember, this here is good for the x coordinate of the end-effector, and then if we repeat this again for the y coordinate and the z coordinate, that would give me 3 equations. Each one of them would define x and y and z trajectories at any moment in time. The third segment for the linear trajectory for Cartesian coordinates of the end-effector would be the alpha, beta, gamma orientation coordinate trajectories. So these alpha, beta, gamma are the 3 primary angles of rotations about x, y, and z coordinates, and they are represented by the rotation matrix that we have in our transformations. Now remember, these the elements of the rotation matrix are nonlinear elements. They include cosine and sine. So basically, these are correlated and they are non-linearly correlated. So we cannot just divide them to via points the way we did in the previous slides. So the methods that we used previously do not apply here. And simply, if we need to find the rotations or orientation trajectories for our end-effector, first thing we have to do is we have to find the rotation matrix, which represents the orientation change between the initial and desired orientation. So remember, we have t initial and t final, and the rotation initial and rotation final would have some kind of a rotation between the two. So we need to find the orientation change, and that would be translated into a single angle, single axis equivalent. Okay, so that rotation matrix would be transformed into single angle, single axis. And then the previous method can be used now or applied at the single angle. So we can divide the single angle into via points, or we can create an equation for that single angle as a trajectory for that single angle. And then afterwards, we can translate again each trajectory step back into a rotation matrix. So once we have our trajectories, either equation or via points for the single angle, then we can change each one of these trajectory points into a rotation matrix that would represent our trajectory for the Cartesian orientation coordinates. Now, for this method, I'm just going to go on the following slides. I'm going to go straight through the equations without discussing how they came about. But if you need more information about how these equations are generated or derived, you can refer to this reference here, Robot Manipulators, Mathematics, Programming and Control by Richard Paul, and this is from the MIT Press in 1981. Now I divided the method here into steps. The first step here is find the rotation matrix between the initial and final rotation matrices. So we're going to have R initial and R final, and we can take these out of the initial transformation matrix and the final transformation matrix of the end-effector. And then we need to find the rotation matrix between these two R's. Okay, so to find the rotation matrix between the initial and final rotations, we multiply R initial transpose times R final. So that gets me a rotation matrix that would have 9 elements, R11, R12, and so forth. The second step, find the single angle representation of R. So now once we have R, okay, we can just substitute in the elements of R in this equation. So this equation finds me the single angle, which I called here phi, which is A tan 2. Again, this equation is in MATLAB, A tan 2, and it has two arguments. The first argument here represents the sine of phi, and the second argument represents the cosine of phi. All of these elements are taken from the rotation matrix R that we found here. So basically R32 is the third row, second column of that rotation matrix. So that would put the element here. So if we substitute this, we can find phi, which represents the single angle for our rotation matrix. Third step, we can find the single axis representation of R. And just for simplicity, I'm going to use S phi as sine phi, and C phi as cosine phi, and V phi as 1 minus cosine phi. Now, here we have several different cases to find the single axis. If phi is close to 0, it's not quite 0, but it's close to 0, then we can assume k to be 1, 0, 0. And again, you can look at the derivation of this and justification of this using the reference book that I talked about in the previous slide. Okay, now if phi is between 0 and 90 degrees, again, we already found phi here. Okay, if phi is between 0 and 90 degrees, then k equals to this quantity, 1 over 2 sine phi, and then the difference between these elements from the rotation matrix. And then if phi is more than 90 degrees, then k equals to this quantity here, which is 1 over square root of v phi. V phi is defined right here. And then here, I will pick only the sign of these differences here. So I take the sign of R32 minus R23. Whatever the value is, I don't care about. All I care about is the sign. If the sign is positive, I keep this positive. If it's negative, I put negative here. And this is the quantity that I would place in this particular place. So this will be the square root of R11 minus cosine phi, and so forth. So this first part of this expression here is only a sign, whether it's negative or positive. And then this would be a quantity that we can put using R from the rotation matrix, and then cosine phi that we already have from here. Okay, now here I have also three cases. If kx is more than ky and kz, so I'm looking here at kx, which is the highest value. If k is higher than ky and kz, then I will have to change ky and kz to become these quantities. Okay, after finding these kx and ky and kz from here. Now, if ky is the highest quantity, which is higher than kx and kz, then I'll have to change kx and kz to these quantities. And if kz is higher, the highest one among the three, higher than kx and ky, that means I'll have to change kx and ky as such here. Okay, so all these conditions here, if followed, then I'll find the single axis representation of the rotation matrix. So by the end of this step, I have the single angle, which is phi, and the single axis, which is k in this case, that represents the rotation matrix, which is the difference between the initial and final rotation matrices that are given. And again, if you need more information about how these are derived, you can go back to the reference that I provided in the previous slide. The fourth step is generate the orientation trajectory delta angles. And I call them delta angles because they are angle differences. So there are differences between one step and another. So at this point here, we have to differentiate between discrete trajectories or continuous trajectories. If we're looking for discrete trajectories with n steps, so we're given n steps, then the step angle would be phi step equals to phi divided by the number of steps. And I guess in this case, the trajectory delta angles, and again, I call this delta angles, are 0, phi step, 2 phi step, 3 phi step, all the way until we reach phi. Okay, so phi is the angle that we have found in the previous slide. Now, if we are looking at continuous trajectories or lines, equations of lines instead of via points, then we are given a total number of seconds or time, total time. And in this case, we can find phi dot, which is equal to phi divided by total time. And in this case, the acceleration phi double dot equals to 0. Now we're ready to find the trajectory delta angle equation. In this case, phi equals to phi dot times t. So if at any moment in time we are given t, we can multiply it by phi dot to find where the single angle is at that particular time. The fifth step for this procedure is to convert each of the orientation trajectory delta angles back to delta rotation matrices. And again, I emphasize here calling this delta angles and delta rotation matrices. And simply because these are difference between angles or difference between rotation matrices. Okay, so we need to do this for each step. And here again, for short, I put S phi as sine phi, and C phi as cosine phi, and V phi as 1 minus cosine phi. Okay, so that delta rotation matrix is defined as follows. Delta Rj, that represents phi j, and phi j basically is the trajectory delta angle that we are taking for that particular step in the trajectory that we found from the previous slide. Okay, so we have all the elements here that we need for this matrix to be constructed. Kx, ky, kz, and then v phi, cosine phi, all of these are defined here. So if we construct this delta r, or delta rotation matrix, then that would give me a rotation matrix that represents the orientation difference in my trajectory. Now, this rotation matrix here, it calculates a single trajectory point. So I need to repeat this for each point in my discrete trajectory if I'm using this discrete trajectories. Okay, and then at the end, I will construct my trajectory differences as follows. So we have here delta R1, delta R2, delta R3, all the way until we find the last delta, which is delta R n plus 1. All right, where n, of course, is the number of steps for our discrete trajectory. Now, if we are looking for continuous trajectory, then we have to repeat that delta rotation matrix right here for each continuous trajectory point. So if we're required to find the trajectory point or where the rotation is at any particular time, then we get that time and we substitute it into the equation for that particular trajectory to get that particular delta phi or phi delta angle difference, and then we substitute that delta phi in here to find delta r. Okay, and then the final step, step number 6, is construct the resulting orientation trajectory rotation matrices. So r trajectory equals to r initial multiplied by delta r1, and then the next step will be r initial multiplied by delta r2, and then we keep going until we get to r initial multiplied by delta r n plus 1. Now that would be my rotation trajectory for the end effector in my Cartesian space. Okay, this is not my rotation trajectory. This is only rotation differences in my trajectory, and here I'm constructing my rotation trajectory from the initial rotation matrix to the final rotation matrix.